Hello everyone. Today I want to talk a bit about the advantages and caveats of doing randomized benchmarking with random quantum circuits. So we recently published in detail analysis of this setting, and I want to show you a few of the general results we obtained. So this is joint work with Ingo Roth from the Technology Innovation Institute in Abu Dhabi and Martin Kliesch from the University of Technology in Hamburg. So they're both here, so feel free to also ask them anything you like. So randomized benchmarking fits into the framework of what is called quantum system characterization. And here we think of a quantum device as in the following way. So we have some kind of classical control system that allows us to perform operations on our device. And we want to do this in some controlled manner and measure in the end. And from this measurement data, we would like to infer some information about our device. So this information can happen on various levels, so on a logical, physical level, and can be very different. But overall, the goals of quantum system characterization is to first convince skeptics that we actually build a useful quantum device and not just like through some dice. So we want to build trust, and we also, of course, we want to learn a bit for ourselves. So, for instance, we want to characterize the gates that we did, and maybe also improve them. And we also want to do benchmarking, meaning that we want to ideally be able to compare our device to others. And in the end, we can use all of this also for calibration. So we can feed it into a feedback loop, for instance, and do some automatic calibration for our gates in the lab. So overall, there are like plenty of characterization protocols, and if you want, you can kind of like characterize them by some properties. And here you have a two-dimensional map. On one axis, you have information gain, and on the other axis, you have assumptions. And so if you want to, usually if you want to learn a lot about your system, you also have to pay for that in terms of the number of measurements you have to do. And in this context, we talk about sampling complexity of a protocol. And so if you want to learn a lot about your system, you usually have to rely on tomographic methods. On the other hand of the spectrum, here is randomized benchmarking, which will be the focus of this talk. So it gives you comparably little information, but also doesn't need so many measurements. And with our work, we also push this a bit to the weaker assumption side, I would say. So overall, let me quickly talk what the idea of randomized benchmarking is. So the idea would be to perform a fancy identity on the system, but we want to do this in a way where we can control the circuit depth. So what we are doing mostly is basically applying a sequence of unitaries U1 to UM, which we subsequently invert in the end. And then in the ideal world, we would then find the system in the initial state with probability 1. Of course, in reality, this does not happen, so this probability is strictly less than 1. And what we moreover would expect is that if we increase m, so the number of unitaries here, then the noise would also pile up and we would get a smaller probability. And in fact, if we do an experiment like this, then what we would see is exponential decay of our probability. So note this is a log scale, and we could then fit this decay to get something like a decay rate that quantifies the performance of our device. So there's a certain standard setting, if you like, where you take these unitaries to be uniformly sampled from the Clifford group. So this has a couple of advantages. For instance, there's lots of papers about this that guarantee the exponential signal form for this protocol for a wide range of noise models. And there's also like a practical advantage of doing that, namely Cliffords are comparably easy, so the inversion gate is again Clifford. You can efficiently compute it, and it has a depth which is independent of the number of Clifford unitaries you've done before. So it's all very nice and so on, but there are some problems with this standard Clifford approach. Namely, you cannot really do it in practice on larger systems. So why is this the case? Multi-qubit Clifford gates require linear depth to be implemented. And this means that just if you have systems with more than a few qubits, these multi-qubit Clifford gates have like a really bad fidelity. And this in practice leads to a very quick decay. So this decay will be so quick that this will be really hard to actually resolve it. So you will need a lot of measurements. And now we could argue, okay, if multi-qubit Clifford gates are just too complicated, let's do something simpler, maybe just like some generators which have constant depth. But in the end, you still will have the inversion gate, which will blow up your circuit and may even be challenging to compute if you go beyond Cliffords. In my opinion, there are even more problems of conceptual nature. For once, the compiler is an essential ingredient of the benchmarking protocol. So multi-qubit Clifford gates have to compile to native gates, and how well this compiler works is like a critical component of your benchmark. And especially in the NISQ era, Clifford gates are not really special, so why should we use them in the first place? So what could we do instead? So what we propose is a protocol that we call filtered randomized benchmarking. And here we take kind of a pragmatic approach. So for your device, you have some native gates, you would like to use them. So build a random circuit out of them. For instance, you could do a brickwork circuit like depicted here. And then you increase the number of layers that you want to do in the circuit. In the end, just do a basis measurement, no inversion. And from the data that you obtain in the basis measurement, you do a classical post-processing. And here the post-processing will depend on a parameter that we call lambda, and I will talk about this in a second. And what you would get then is again a signal, depending on the length of the sequence, or the number of layers if you like. And without noise, nothing spectacular is happening. So after like a short while, you will see a constant signal. But if you add some noise to the system, you will again get exponential decay. So this is again a log scale. So after a short while, like let's say around here, you can nicely fit this with an exponential decay. And now we get some decay rates that depend on this parameter lambda, and you can report them. So that's the idea. Everything here is spam robust, as it should be. And now I will talk a bit about this lambda parameter. So this is a bit, delicate, I would say. So in principle, you're doing random circuits, but these random circuits, they live in some group. So in principle, you will generate a group by just doing random circuits. And what's important for randomized benchmarking is the representation theory of this group. So you have a representation of this group on linear operators, just given by normal conjugation. And you can reduce that into irreducible sub-representations, and that's the things that we label here by lambda. So basically, for every of these errors, you do a different kind of post-processing, and that's how it works, basically. But now I also have to tell you somehow what the post-processing is. So let me do this now. So pictorially, you have this kind of picture. So you do some random sequence of gates. And you measure, you sample these gates from a measure on your group. So this could be just a random circuit that we described. And you observe some samples from this outcome distribution. So we want to use these samples to estimate a function. And this function, we call it this capital F lambda here. You could call it a fidelity or whatever you like. It's an expectation value over the measurement samples and the random sequences of what we call a filter function small f lambda. And this filter function involves basically the ideal circuit, so the noise-free circuit. And we use the letter omega here to denote the unitary channel, like the ideal unitary channel. And but there are some additional objects here. So there's like a p lambda and a s to the -1. If I would leave those out, this would just be the ideal Born probability. But so this p lambda here is a projector onto this irrub that we're interested in, which basically isolates the contribution to the overall signal coming from this irrub. And then there's something slightly more complicated, which is the inverse of what we call a frame operator. So this frame operator is well known in tomography, for instance. There you use this object to reconstruct the final state of your circuit from measurement data. And we do a similar thing here, actually. So let me do a quick example. Linear cross-entropy benchmarking, which might be known to some of you. Here, there is here the group that we consider is the unitary group. And it's well known that its representation on linear operators splits into two irreps, namely the trivial one, which is supported on the identity matrix, and the adjoint representation, which is supported on the traceless subspace. And so to make this decomposition, you can choose, for instance, the Pauli or while basis. And if you do this, you can also write out this frame operator very easily because it's simply diagonal. And it will be 1 on the trivial irrep and d plus 1 on the traceless irrep. So now we can plug this into the filter function. And we get a d plus 1 from the inverse frame operator. And from the projector, we get this square bracket here. And here we can already see that we get basically the ideal Born probability, which I denote here by P ideal. And we can take this expression and plug it into our fidelity. And we can identify this green bracket there exactly with the expression that you would get for cross-entity benchmarking. So we see that basically the fidelity that we defined for filtered RB is up to a constant, which is for larger dimensions close to 1, equal to the cross-entity benchmarking fidelity. So if you like, you can understand filtered RB as a generalization of linear cross-entity benchmarking. Okay. In generality, we have some compact group, and it decomposes into irreps. And we sample gates from some measure for our sequence. And what we want to assume is that this measure is gapped. So we have a spectral gap, which basically means that eventually our random circuit will produce random gates. And we have an irrep dimension that we're interested in. Then we have a theorem that looks basically like this, which the expected signal is epsilon close to an exponential decay if we choose our sequence length large enough. And here large enough basically means, well, basically the position of this gray line up there. And the lower bound that we obtain is given by the inverse spectral gap times the logarithmic dimension, roughly. So let me do an example. If you have a unitary 2 design, for instance, the Clifford group or the unitary group, and you use brickwork circuits, then the lower bound is basically 9n, something like this. So and this comes from the inverse spectral gap and can probably be improved a bit in this setting. So this might be a good time to talk a bit about the technique behind all of this. So we have seen basically that in a noise-free setting, the Born probability is just given by the representation of our group. So the unitary channel that we actually want to apply. But if we have noise, we get a bit of a different scenario. So we change the initial state and the measurement by some noisy versions, and we change the representation for something that we call an implementation function. So this could be some function on our group. It just may be completely positive and trace non-preserving, non-increasing. But it's gate-dependent noise, but it should be Markovian and time stationary. That's what we assume for our work. Then if you plug this in, you find that the fidelity has a rather simple expression. I mean, it's a lot of simples, but it's rather simple. Namely, it involves the power of some operator there in orange. And this operator can be understood as it has a form of a channel twirl, if you like, where we replace the representation on the right-hand side with your noisy implementation phi. So think about it a bit as a noisy channel twirl. So there's some relation to harmonic analysis. That's why we call it Fourier transform, but it should not be too important right now. And so you take powers of this noisy channel twirl and you apply it on the dephasing channel in the computational basis, and then you contract it again with states basically. So that's what the signal looks like ideally. But what you can see here that everything is linear in this orange operator. So what you actually see is are powers of the eigenvalues of this operator. So you could argue that filtered RB exposes powers of these eigenvalues. So it's kind of a power method. So on a technical side, what we now have to do is basically to bound these eigenvalues somehow, because we don't assume anything about this implementation. We rely to perturbative methods. In a noise-free setting, basically, if we have omega instead of phi, we can actually get a channel twirl, and this has a form of a moment operator. So it has a block structure, has a 1 up there and some lower right block, and the norm of this lower right block is exactly 1 minus the spectral gap. And now, if our implementation is not too bad and it's somehow close to the ideal one, then we can do some perturbation theory to show that basically the noisy channel twirl is also block diagonal. And if you plug this in the above methods and lower and upper bound contribution given by the lower right block, then we get the claimed sequence bounds. So this is just a teaser. Of course, it takes a bit more analysis to do this. But the nice thing is that you can also do this perturbation theory to obtain sampling complexity bounds. So here we consider a single-shot estimator for our fidelity, meaning we sample exactly once per random circuit. So we measure once per random circuit. You could also analyze other estimators, but in a similar fashion, but you will find out that their variance will actually be larger in general. So for this single-shot estimator, we get a sampling complexity theorem, namely this looks a bit similar as before. So basically, if you choose the sequence length double as large as before, then we get an epsilon close approximation with high probability if the number of samples fulfills this like lower bound here. And here, an ideal is the number of samples that you would need in the absence of noise, and if you would sample H randomly. So this looks a bit convoluted, so let me do another example. So if you have a unitary free design like the Clifford group or the unitary group, it's very well known that this an ideal here, you can compute it using some H integrals, is 3 over epsilon squared delta. And now the theorem says that even if you add noise and if you sample non-uniformly, the worst thing that can happen is that your enumerator gets modified by some alpha. And by choosing the sequence length, you can actually make this alpha arbitrarily small. But here it would also be fine to just choose alpha equals 1, for instance. Okay, let me conclude this talk. So there's still some open problems in that we would like to solve. So for instance, we have seen that for universal or Clifford random circuits, we actually need linear depth. So this might be unsatisfactory, but it's kind of, there's no way you get around this. If you use smaller groups, then you can actually get constant depth. So if you want to get sublinear depth, we actually propose to make some changes to this filter function, so changes to the post-processing. And we show that basically in the ideal setting this works, so you get it works in constant depth, but you cannot so our rigorous methods that work before, they need some non-trivial extensions to work for this setting. But we still think it's highly relevant. These proposals are highly relevant because the similar problems were recently discussed in the gross entropy benchmarking literature under the name of unbiased versus biased estimators, and I think we have some new input to this discussion with our proposals. And in the end, we think that this perturbative treatment that we do is actually generally applicable if you deal with noisy circuits in some application, and therefore might also be very relevant if you're just interested in the technique. And with that, I want to conclude and thank you for your attention.
Awesome, thank you, Markus. Are there any questions, speaker?
Thank you for the talk. So, in general, is it difficult to compute the frame operator?
So the thing is basically that it's a good question. In general, it's very difficult to compute a frame operator, and so you would need to do this, for instance, in shadow tomography. And there have been a couple of papers on this, but we do a trick basically here. We consider the H random frame operator. So basically that you would get for H random gates, and then you can do some representation theory. It's not so hard, but that's basically why we require this linear depth, because you have to be close enough to being hard random to cancel out this frame operator. That's basically the reason. Yeah. Yeah.
Thanks for the talk.
Yeah.
So what is this quantity that you're estimating? Is it related to the average gate fidelity? Like if I have like Clifford and T gates, both of the gates in my gate set.
Yeah.
In the GIs that you consider.
I mean, it's very simple to standard RB. So basically, so the decay rate you obtain, you can translate it to some average gate fidelity of some noise in between gates in some gauge and so on. But you know, the whole discussion about gauge freedom in randomized benchmarking also applies here. So it's not straightforward to interpret this decay rate in terms of some physical quantities. So you can make some interpretation, but the usual caveats apply, so to say. Yeah.
And one last thing, do you have restrictions on the GIs that you can take, like the representation? Do you have restrictions on the set of GIs or the set of native gates that you can allow in this framework?
Sorry, on the representation or on what?
Is there any restrictions on the set of GIs that I can consider, the random gates? Or can it just be anything?
Yeah, they have to come from some compact group. So that's the restriction we have, and the measure should be gapped so that you actually, you know, if you do a random walk on your group, then you should cover the whole group. Yeah, that's what we assume, but in principle, that's it. Yeah. Yeah.
Okay. Thank you.
Hi. Thanks for a very nice talk. It's related to the previous question. So, is it possible to bound the depth of approximate T design, for example, in your case?
So the spectral gap bounds the depth of or the convergence of approximate T designs. Is that what you're asking about?
Yes. So in your case, you are bounding for example, the 3 design Clifford, the minimum depth of the random Clifford, and is it also possible to extend to approximate T design random unitaries?
Yeah, the whole thing is about approximate designs. Okay. So you take some random circuit which will be an approximate design, and the spectral gap quantifies how fast you converge to how fast your design converges. So yeah, basically the whole point is that you want to do RB with approximate designs, if you like.
Okay. Yeah. Thank you.
Mm-hmm.
Hey, yeah. Hi Markus, thank you for the nice talk. I want to say, so you assume the noise is gate dependent, Markovian and time stationary. Is that right?
It's gate dependent, Markovian and time stationary. Yeah.
Is there any? Can you say anything about? Suppose you can sort of bound the amount of drift or something, or the distance from Markovianity. Is there any kind of robustness to the?
Yeah, so there are some possibilities to include non-Markovianity. So by just, for instance, modeling some environment or like some memory explicitly, and there has been some recent paper about but I have to recall the title. So so I think it's possible to go to non-Markovianity. Should not be hard, but with time drifts, I'm not so sure. I think you can also bound this. You can include this, model this, but I'm not so sure if the results hold up. You know.
Okay. All right. Yeah. Thank you.
I think we might have time for one more question, if there's any others.
Hi, have you ever considered the coefficient of the largest eigenvalue equals 0? So your exponential decay actually didn't depend on the largest eigenvalue.
Yes. But you ask about the coefficients, so the spam, the spam coefficients, you mean?
Also considered the coefficients.
Yes. So we have a formula for the coefficients. I mean, so they're spam dependent, like basically for normal RB. But they have a nice interpretation. Basically, these coefficients, which is so they're basically related to the noise-free situation. So like basically the fidelity you would get with noise-free circuits, so to say.
Okay, so which means now you suppose with the sparm noise free model, the coefficients is not equal 0, right?
0?
Yeah, I mean, since you use a sparm free noise, sparm robots assumption model, so I guess you assume the coefficients did not equal 0.
Yeah. So in principle, you could like come up with a situation where the coefficients vanish. That's right, and then you will not see a signal. But I would call this like a very either ill-designed protocol or like very malicious device that you have. So I think in practice this doesn't play a role.
Thanks.
Do you know what I mean? You can also ask like later if you like.
Thanks.
Yeah.